Bismillahirrahmanirrahim. Welcome back with new lecture 10 in discrete structures. This is a series which we have discussed all topics of discrete structures. Now we are at lecture 10. In the previous lecture, I discussed some slides from the previous lecture to remind for the next lecture. We have discussed already change of the variable. We observed that summation k square. This was also discussed in the previous lecture, but I remind here to recall for the new lecture. K square is equal to, we write in this form, and I square summation I square, I varies from 1 to 3 is 1 square plus 2 square plus 3 square, and so all these two summations are equals. The equation illustrates the fact that the symbol used representing the index of summation can be placed by any other symbol as long as the replacement is made. The sequence or the consequence, the index of a summation is called a dummy variable, and a dummy variable is a symbol which I have already discussed. And it's also transforming a sum by a change of a variable. How we change the sum to a variable? This is the example. The summation k varies from 0 to 6, 1 over k plus 1. Change of variable j is equal to k plus 1. We change here. So first we calculate the limits. When k is equal to 0, then j is equal to 1, and when k is equal to 6, j is equal to 7. And so the new limits are 1 to 7. The previous limits are 0 to 6. So we put the new limits and calculate where j is equal to k plus 1. So we find k is equal to j minus 1. So we put the value of k in the terms of j. So we obtained this summation as 1 over j. J varies from 1 to 7. And this is here is the example. Change of the variable as k over k n plus k, where change the variable j is equal to k minus 1 is the same. And here is the new part, second part. We transfer the summation obtained in the part A by changing all j's to k's. So we put k is equal to 1 and we find the values of j's. So the new limit is j is equal to 0 and j is equal to n. Now we replace this k over n plus k. It's equal to j plus 1 over n plus j plus 1. And so the general term of new summation is j plus 1 over n plus j plus 1. And now, and in the second part, we changing all the j's to k's. The right hand side of this equation, this will become k. We replace the values of k with j's, so this will become 5.1.4. So this will become k plus 1 over n plus k plus 1, and when we combine these two terms, this will give the answer, this equation. And this was the factorial notation which we have discussed in the previous lecture. For each positive integer, n factorial is defined as n into n minus 1 up to 1. So it's also a recursive definition of the factorial is n factorial is equal to 1 if n is equal to 0, and if n greater or equal to 1, then this will become n into n minus 1 factorial. The next example illustrates the usefulness of the recursive definition of making computations. For example, if we say 5 factorial, then it means 5, 4, 3, 2, 1. Similarly, we can also say that 5 factorial is equal to 5 dot 4 factorial, and 4 factorial is equal to 3, 2, 1. So here is the example of some first 10 factorials. 0 factorial is 1, 2, 1 factorial 1, 2 factorial, 3, 4, and 5 factorial. Next is the example of computing with factorials. These are the examples. We have to compute these factorials. 8 over 7 factorial. We calculate this. We can write 8 factorial as 8 into 7 factorial over 7 factorial. So we cancel out these factorials, so this will become 8. Similarly, the other examples can be solved in the next slide. Here we have solved 5 over 2 factorial, 3 factorial, and the C part 1 by 2 factorial plus 1 over 3 into 3 factorial. We make first of all the denominator of these two terms same, so that we can easily solve these two terms. We can also solve by by expanding all the factorials, but to make smart calculation you can easily solve by this method. And and for n plus 1 factorial over n factorial, n plus 1 into n factorial over n factorial, so we cancel out these n factorial, so this the answer will be n plus 1. And similarly for n factorial over n minus 3 factorial, we easily solve. We reduce it to up to n minus 3, so we can cancel out, then the answer is n into n minus 1 and minus 2. And in some special factorial cases, NCR combination and choose R, you can also see that these are the definition of this is NCR is equal to n factorial over R factorial into n minus R factorial. So we can easily solve. Here is the example 3 combination 2. So this is 3 factorial over 2 factorial into 3 minus 2 factorial. There is example of computing NCR by hand, so we can easily solve this. 8C2. 8C2 means 8 factorial or 8C5. 8 factorial into 5 factorial into 8 minus 5 factorial, which will become 8 factorial over 5 into 3 factorial. Now we can calculate these factorials easily. Similarly, for 4C4, it means 4 factorial over 4 factorial into 4 minus 4 means 0 factorial, which will become 0, or 0 which will become 1. So the answer is 1. Similarly, for n plus 1, C n. I shortly brief this slide because we have already discussed these two. Now we will discuss about the mathematical induction, which is very important in the discrete structures. We will discuss about the principle of mathematical induction, method of the proofs, finding terms of sequences, sum of geometric series, and first here introduction about the mathematical induction 1, and next in the next lecture we will discuss about the mathematical induction 2. Any whole number of cents of at least 8 cents can be obtained using 3 cents and 5 cents coins. More formally, for all integers n which are greater or equal to 8, n cents can be obtained using 3 cents and 5 cents coins. Even if we more formally we said for all integers n greater or equal to 8, P of n is true, where P of n is the sentence saying that n cents can be obtained using 3 coins and 5 cents coins. Here is the number of cents. How to obtain it? 8 cents. We obtain these by 3 cents plus 5 cents. If we say about the 9 cents, then this will become by 3 plus 3 plus 3. And if we want to obtain the 10 cents, then this will be obtained by 5 plus 5. Similarly, for 11, we can obtain by 3 plus 3 plus 5. And for 12 cents, we can obtain it by 3 plus 3 plus 3 plus 3. And for 13, we will obtain by 3 plus 5 plus 5. And for similarly for 14, we can obtain by 3 plus 3 plus 3 and plus 5. Because we have the combinations of 3 and 5 cents only. If we want to obtain the 15 cents, then 3 times of 5 coins, by adding these we obtain this. And if 16 coins, you can obtain it by 3 plus 3 plus 5 plus 5. And similarly for 17, you can obtain it by 3 plus 3 plus 3 plus 3 plus 5. And if we want to obtain 24 coins, then 3 plus 3 plus 3 up to 8 times. The cases shown in the table provide inductive evidence to support claim that P of n is true for journal n. Indeed, P of n is true for all n greater or equal to 8 if and only if it is possible to continue filling in the table for arbitrarily large values of n. The kth line of the table gives information about how to obtain the k coins using 3 and 5 coins. Continue the table to the next row. Directions must be given for how to obtain k plus 1 cents using 3 and 5 coins. The secret is to observe to obtain k plus 1 cents using 3 and 5 coins. The secret is to observe first that if k coins can be obtained using at least 5 cents coins, then k plus 1 can be obtained by replacing the 5 coin by 2 3 coins. So here is the diagram. If there are these 3k coins and this 5, replace 5 coin by 2 3 coins. Add these two, then these are k plus 1. If on the other hand, k is obtained without using 5 and 3 coins are used exclusively, and since the total is at least 8, 3 or more 3 coins, so it must be included. 3 of 3 coins can be replaced by 2 5 coins to obtain a total of k plus 1 coins. Any argument of this form is an argument by mathematical induction. In general, mathematical induction is a method for proving that a property defined for integers n is true for all values of n that are greater than or equal to some initial integer. So this is the diagram to show the example. And now the principle of mathematical induction, we say that let P of n be a property that is defined for integers n and let k be a fixed integer. Suppose the following two statements are true. P of A is true for all integers k greater or equal to A. If P of k is true, then P of k plus 1 is true. Then the statement is true for all integers n greater or equal to A. P of n is true. So if you can say this k domino falls backward, it pushes up to the k plus 1's domino backwards. So it's first, second, if this will drop at this will uh, falls on this. So at the end, k will drop at k plus 1. Next, we have to discuss about the method of proof. Method of proof by mathematical induction, we consider a statement of the form for all integers n greater or equal to a, the property P of n is true. To prove such a statement, perform the following two steps. Step 1, basic step, is the show that P of A is true. And step 2, inductive step, show that for all integers k greater or equal to A, if P of k is true, then P of k plus 1 is true. To perform this step, suppose that P of k is true, where k is any particular but arbitrary chosen integer with k greater or equal to A. This supposition is called the inductive hypothesis. Maybe you have discussed it in your statistical course. This supposition is called the inductive hypothesis. Then we show that P of k plus 1 is true for all k greater or equal to A. Uh, Here is defined in terms of the sequences proposition. For all integers n greater or equal to 8, n cents can be obtained using 3 cents and 5 cents coins. Let the property P of n be the sometimes n coins can be obtained using 3 and 5 coins. So this is P of n. Show that this statement P of n is true. P of n is true because it coins can be obtained using 1 3 coin and 1 5 coins. We show that for all integers k greater or equal to 8, if P of k is true, then P of k plus 1 is. Show that for all integers, we suppose that k is an integer with k greater or equal to 8, such that k coins can be obtained using 3 coin and 5 coins. So this is P of k. Inductive hypothesis. Explicit formula. Uh, in case 1, there is a 5 coin among those choose to make up the k coins. In this case, replace 5 coin by 2 3 coins. The result will be k plus 1 coins. In case 2, there is not a 5 coins among those choose to make up to the k. In this case, because k is greater or equal to 8, at least 3 coins can be must have been used. So remove 3 coins and replace them by the 2 5 coins. The result will be k plus 1. Thus, in either case, k plus 1 can be obtained using 3 and 5 coins. You can say 9 coins, 3 plus 3 plus 3, and we discuss about the 10 coins, then it will become by 5 plus 5. Propositions for all integers n greater or equal to 1, p of n 1 plus 2 plus up to n, this will become n into n plus 1 by 2. So if it can also be proved by this example 1 plus 2 plus 3 up to 10, where n is this is n. So this will become 10 into 10 plus 1 by 2, which is 55. Here a is 1, first term. Show that we show that it p of 1 is true. It's true for 1. To establish this, we must show that 1 is equal to 1 into 1 plus 1 by 2. So, but the left hand side of this equation is 1 and the right hand side is also 1. So, p of 1 is true for n is equal to 1. We show that for all integers k greater or equal to n, if p of k is true, then p of k plus 1 is also true. So maybe you can use in your pre-calculus that p of k is true for a particular but arbitrary chosen integers. That is, suppose that k is an integer with k greater or equal to 1, such that 1 plus 2 plus 3 up to k, this will become k into k plus 1 by 2. We must show that p of k plus 1 is true. That is, we must show that 1 plus 2 plus 3 up to k plus 1 is equal to k plus 1 into k plus 1 by 2. Or equivalently, we can show it k plus it's equal to k plus 1 into k plus 2 by 2. For this is for p of k plus 1. We will show that the left hand side and the right hand side of this proposition are equals to the same quantity and thus for equal to each other. Mean to say, you can see that there are three steps. First of all, we prove it by the mathematical induction means we prove it for n is equal to 1, then n is equal to k, and then we prove for n is equal to k plus 1. Left hand side of p of k plus 1 is 1 plus 2 plus 3 plus k plus 1. This will become 1 plus 2 plus 3 plus k plus k by making the next two last term explicit. Then this will become, this answer will become k into k plus 1 by 2, and this is the same. And if we add these two terms, we here divide and multiply it by 2, then it will become 2 into k plus 1 over 2. So the answer will become k square plus k by 2 plus 2k plus 2. If we solve it by algebra, we take the LCM, then this will become k plus 1, k plus 2. The answer will be k square plus 3k plus 1 by 2. And the right hand side of the p of k plus 1 is k plus 1 into k plus 2 by 2 is equal to k square plus 3k plus 1 by 2. Thus the two sides of p of k plus 1 are equal to the same quantity, and so they are equal to each other. Therefore the equation p of k plus 1 is true as was shown. Since we have forwarded both the basis steps and the inductive steps, we conclude that the theorem is true. P of n is true for all If we summarize this theorem, as I have already discussed in previous slides, there are three steps for n is equal to 1, n is equal to k, and n is equal to k plus 1. We prove for all these values. Now we discuss about the sum of geometric series. For any real number r except 1, and any integer n greater or equal to 0, summation I varies from 0 to n, Rn plus 1 minus 1 over R and R minus 1. We prove it by mathematical induction. Suppose R is a particular but arbitrarily chosen real number that is not equal to 1, and let the property P of n be the equation. Summation I varies from 0 to n, it's equal to Ri plus 1 minus 1 over R minus 1. So this is the proposition here. We must prove P of n is true for all integers n greater or equal to 0. We do this by mathematical induction on n. We show that P of n 0 is true. To establish P of 0, we must show that I varies from 0 to 0. This will become R 0 plus 1, and so this is P of 1. And the left hand side of this equation is R0, which is equal to 1, and the right hand side is R0 plus 1 minus 1 over R minus 1, which is R minus 1 over R minus 1, so this is 1. And also because R1 is equal to R and R is not equal to 1, hence P of 0 is true. We show that for all integers k greater or equal to 0, if P of k is true, then P of k plus 1 is also true. Suppose that P of k is true for a particular but arbitrarily chosen integer k greater or equal to 0, that is, uh, let k be an integer with k greater or equal to 0, and suppose that summation I varies from 0 to k is equal to r k plus 1 minus 1 over r minus 1. We must show that P of k plus 1 is true. That is, we must show that I varies from 0 to k plus 1. We put in the original statement. So this r k plus 1 minus 1 over r minus 1. Or equivalently, you can say that this will become r power k plus 2 minus 1 over r minus 1. So this is P of k, and this is P of k plus 1. Now we solve this. I varies from 0 to k plus 1, Ri plus Rk plus 1, where I varies from 0 to k. So this will become Rk plus 1 minus 1 over R minus 1 plus Rk plus 1 by substituting from the inductive hypothesis. Now by multiplying these two terms, we obtained this R minus 1. You can say uh, we uh, uh, we divide and multiply in this expression r minus 1 to make the same denominators, so that we make by adding these fractions we take LCM. So this will become rk plus 1 minus 1 plus rk plus 2, because here r is 1, minus rk plus 1 when we multiply this term by this 1. So this will and the denominator is r minus 1. So this will become rk plus 2, and we cancel out these two terms. So rk minus 2 minus 1 over r minus 1. So which is the right hand side of p of k plus 1. as this was to be shown. Now we discuss about the reduction additional formula, reducing the additional formula, applying the formula for the sum of geometric sequence in each of the part AB. Below, assume that m is an integer that is greater than or equal to 3. Write each of the sums is closed into closed form. 1, 3 square plus 3 raised to the power n minus 2. We solve this part A. The solution is like this, which is equal to 3 raised to the power m minus 2 plus 1, this is k plus 1 minus 1 over 3 minus 1. Now applying the formula for the sum of geometric sequence, r is equal to 3 and n is equal to m minus 2. When we simplify this, this will become 3 raised to the power m minus 1 over 2. And similarly for the second part B, we solve it 3 square plus 3 cube plus 3 fourths up to 3n. So we can also write it as 3 square into 1 plus 3 square plus 3 fourths up to so on 3m raised to the power minus 9. So 3 square will become 9 and we put the formula on this 3 raised to the power m minus 2 plus 1. So this will become m minus 1 over 2. As with the formula for the sum of the first n integers, there is a way to think of the formula for the sum of the terms of a geometric sequence that makes it seem simple and initiative. Let Sn is equal to 1 plus r square plus up to so on plus rn. If we multiply r on both sides, then this will become rsn is equal to r square plus r cube. This will become rn plus 1. And when we subtract these two terms, rsn, this from this term, you can say this if this is 1 and this equation is 2, so here is 2 minus 1, so this will become this equation minus this equation, the right hand side, so this will become rn plus 1 minus 1, but rsn minus sn is equal to r minus 1 sn, the left hand side. So equating the right hand sides of the equations and dividing, we can see that Sn is equal to Rn plus 1 minus 1 over R minus 1. We can here you can see that Sn into R minus 1, then this will be divided on the right hand side. Now we discuss about we'll discuss about the mathematical induction 2. In the previous we discussed about the mathematical induction 1, and in this we will discuss about the mathematical induction 2. If we discuss about the topics which we discussed in, we will discuss in this next half lecture, the sum of geometric series, proving the divisibility properties, proving an inequality, and proving the sequence property. An example and the strong mathematical induction is also will be discussed here. Sum of geometric series. For any real number r except 1, for any integer n greater or equal to 0, Ri, summation Ri, I varies from 0 to n, r n minus n plus 1 minus 1 over r minus 1. We prove it by mathematical induction as we discussed in the previous slide also. Suppose r is a particular but arbitrarily chosen real number that is not equal to, and let the property p of n with the equation summation ri, I varies from 0 to n, ri plus 1 minus 1 over r minus 1. We must show that p of n is true for all integers n greater or equal to true. We do this by mathematical induction on n. To show that p of 0 is true, so to establish this p of 0, we must show that summation r I varies from 0 to 1, r 0 plus 1 minus 1 over r minus 1. So this is p of 0. The left hand side of this equation is r naught is equal to r 0 is equal to 1, and the right hand side this will become 1. And so hence, because r1 is equal to 0 r and r is not equal to 1, hence p of 0 is true. Now we show that for all integers k greater or equal to 0, if p of k is true, then p of k plus 1 is also true. Suppose that p of k is true for a particular but arbitrarily chosen integer k greater or equal to 0, that is k be an integer with k plus k greater or equal to 0, and suppose that ri, I varies from 0 to k, r k plus 1 minus 1 over r minus 1 by inductive hypothesis. If we put here, we must show that this will be is true for p of k plus 1. We must show that ri, I varies from 0 to k plus 1, r k plus 1 minus 1 over r minus 1. Or equivalently, we can say that this will become r k plus 2 minus 1 over r minus 1. So this is p of k plus 1. We solve it by putting the terms. So this will become r summation ri, I vary from 0 to k. So this will become this term, and this is the same as rk plus 1 by substituting the values, inductive hypothesis also. And we here divide and multiply by r minus 1. So we conclude it that the answer is r k plus 2 minus 1 over r minus 1. So which is the right hand side of p of k plus 1. So this was to be uh, um, here we discuss about the reducing additional formula. Maybe we already discussed in the previous slide. By applying the formula, the sum of geometric series of 1 plus 3 plus 3 square, so plus 3 raised to the power m minus 2, and in the second part 3 square. We will discuss about the first part. We have already discussed. Also we recall here 1 plus 3 plus this. So by applying this formula, this will become k plus 1. So here is this is k over 3 minus 1. So this will become 3 raised to the power m minus 1 by 2. And in the second part B, it can be written as 3 square into 1 plus 3 square plus 3 raised to the power m minus 2. So this will become 9, and this we use formula for this 3 raised to the power m minus 2 plus 1. So this will become m minus 1 by 2. And as with the formula for the sum of the first n integers, there is a way which we proved in the previous slide. Sn is equal to this rsn if we multiplied r on both sides, and then subtract these two equations rsn minus sn. So this will become r n r raised to the power n plus 1 minus 1, and we take common Sn from these two, so this will become Sn into r minus 1. So r minus 1 is divided on the right hand side. Now here is we discuss about the proving divisibility property. It's very important. The proposition is that for all integers n greater or equal to 0, 2 raised to the power 2n minus 1 is divisible by 3. Let the property p of n be the sentence 2 raised to the power 2n minus 1 is divisible by 3. It means this is p of n. 2 raised to the power 2n minus 1 is divisible by 3. Show that p of 0 is true. To establish p of 0, we must show that 2 raised to the power 2 into 0 minus 1 is divisible by 3, because this we have shown by this by mathematical induction. But 2 into 2 raised to the power 0 minus 1 is equal to 2 raised to the power 0 minus 1, which is equal to 0. Since and 0 is divisible by 3, because 0 is congruent to 3 mod 3 with the quotient 0. Hence p of 0 is true. Now we show that for all integers, for if p of k is true, then p of k plus 1 is also true. Suppose that p of k is true for a particular but arbitrarily chosen integer. So let k be any integer with k greater or equal to 0. Suppose that 2 raised to the power 2k minus 1 is divisible by 3. This is p of k by inductive hypothesis. By definition of the divisibility, this means that 2 raised to the power 2k minus 1 is equal to 3r for some integer r. We must show that p of k plus 1 is true. That is, we show that this will become 2 raised to the power 2 into k plus 1. We replace k by k plus 1 minus 1 is divisible by 3. So this is the proposition of p of k plus 1. So, but you can say 2 into 2 raised to the power k plus 1 minus 1 is equal to 2 raised to the power 2k plus 2 minus 1, which is equal to 2 raised to the power 2k into 2 raised to square minus 1. By the laws of exponents, you can easily expand these terms, which will become 2 raised to the power 2k into 4 minus 1. So this will become 2 raised to the power 2k into 3 plus 1 minus 1. So we can write by the laws of algebra 2 raised to the power 2k into 3 plus 2 raised to the power 2k minus 1. We can separate these two terms. So this will become 2 raised to the power 2k into 3, and this will become 3r from this. Uh, 2 raised to the power 2k into 3 plus 3r. This will become 3 into 2 raised to the power 2k plus r by factorizing by 3. 2k plus 1 is less than 2k. We must show that p of k plus 1 is true. That is, we must show that 2 into k plus 1 is less than 2 raised to the power k plus 1. Or equivalently, you can say that 2k plus 3 is less than 2 raised to the power k plus 1. So this is p of k plus 1. But 2k plus 3 is equal to, you can write here by the algebra 2k plus 1 plus 2. So this will become 2k plus 2k, which is less than. So 2k plus 3 is less than 2 into 2 raised to the power k, which is equal to 2 into 2 raised to the power k, which is equal to 2k plus 1. So this is what we need. This was the step which has to be shown. If we discuss the solution of this, if a1 is equal to 2, a2 is equal to 5, a2 minus 1, so this will become 10, a3 is equal to 5, a3 minus 1, this will become 50, and a4, so this will become 5, a4 minus 1, so this will become 250. To use mathematical induction to show that every term of the sequence satisfies the equation, begin by showing that the first term of the sequence satisfies the equation, then suppose that an arbitrary chosen terms ak satisfies the equation, and prove the next term ak plus 1 also satisfies the equation. Let a1, a2, a3 be the sequences defined for specifying the values. A2 is a1 is equal to 2, ak is equal to 5, ak minus 1 for all integers k greater or equal to 2. And let the property p of n be the equation an is equal to 2 into 5 raised to the power n. We will use the mathematical induction to prove that for all the integers n greater or equal to 1, p of n is true. And show that p of 1 is true. To establish p of 1 is true, we must show that a1 is equal to 2 into 5 raised to power 1 minus 1, which is p of 1. But the left hand side of p of 1 is a1 is equal to 2 by the definition of this. And the right hand side of p of 1 is 2 raised to the power 5 minus 5, 1 minus 1, which is 2 raised to the power 5 into power 0. So this is true. So this is true. But the left hand side is also true, and the right hand side is true. So thus the two sides are equal, and are equal to the same quantity, and hence p of 1 is true. Now we show that for all integers k greater or equal to 1, if p of k is true, then p of k plus 1 is true. Similarly, we repeat the process for p of k, and by the definition of divisibility, you can say that ak is equal to 2 into 5 raised to the power k minus 1. We must show that it will true p of k for p of k plus 1. We must show that ak plus 1 is equal to 2 into 5 raised to the power k plus 1. Or equivalently, ak plus 1 is equal to 2 into 5 raised to the power k, which is, but the left hand side ak plus 1 is equal to 5 ak plus 1 minus 1. It can be written as 5 ak. So you can write it ak is equal to 2 into 5 raised to the power k minus 1. So this will become 2 into 5 raised to the power k, which is the right hand side, and this was to be shown. There is also the examples proof by mathematical induction. Let the property p of n with the equation 1 plus 1 by 1, 1 plus 1 by 2, up to so on, 1 plus 1 by n is equal to n plus 1. Show that the property is true for n is equal to 1. When n is equal to 1, the left hand side of the equation is 1 plus 1 by 1, which is equal to 2, and the right hand side is 1 plus 1, which is equal to 2. Also, the property is true for n is equal to 1. Uh, so we use so if the property is true for n is equal to k, it is true for n is equal to k plus 1. Similar process. So we put if we put k with this the inductive process, we must show that it will be true for n is equal to k plus 1. So this will become 1 plus 1 by 1. So this is 1 plus 1 plus 1 plus 1 by 2. By making the next two lost factorial factor explicit, this by inductive hypothesis, this will become k plus 1 into 1 plus. So by the algebra, this will become k plus 1 plus 1. Next, the problem for each positive integer n, let p of n be the property 2 raised to the power n, which is less than n plus 1 factorial. Alright, p of 2 is p of n is p of 2 is. That's not. Write P of k, write P of k plus 1 in a proof by mathematical induction, that is, for all integers n greater or equal to 2, there must be shown that for inductive hypothesis test. If P of n is equal to P of n 2 raised to the power n less than n plus 1 factorial. P of 2 is true because 2 square is equal to 4, which is less than 6, which is equal to 2 plus 1 factorial. And if we discuss about P of k, 2 raised to the power k less than k plus 1 factorial. And similarly, we have to show about k plus 1, 2 power k plus 1, which is less than k plus 1 factorial. Must show that if k is an integer with k greater or equal to 2 and 2 raised to the power k less than k plus 1 factorial, then 2 raised to the power k plus 1 is less than k plus 1 factorial. So its example also, proposition 7n raised to the power n minus 1 is divisible by 6 for each integer n greater or equal to 0. We prove it by mathematical induction that the property P of n by the sentence 7 raised to the power n minus 1 is divisible by 6. Show that the property is true for n is equal to 0. This property is true for n is equal to 0 because 7 raised to the power 0 minus 1 is equal to 0 and 0 is divisible by 6. And show that we show have to show that for all integers k greater or equal to 0, if the property is true for n is equal to k, then it's true for n is equal to k plus 1. So these are the main three steps. Everywhere when you discuss about the mathematical induction, you have to prove these three steps. One is n is equal to 0, n is equal to k, and n is equal to k plus 1. We must show that 7 raised to the power k plus 1 minus 1 is divisible by 6. By the definition of divisibility, the inductive hypothesis is equivalent to the statement 7 raised to the power k minus 1 is equal to 6. So we you can solve it by this strong mathematical induction. Now let P of n be a property that is defined for integers, and let a be the fixed integers with a less or equal to b. Suppose the following two statements are true. P of a and P of a plus 1 and P of b are all true. Basic steps for any integers k greater or equal to b. If pi is true for all integers I from a through k, then P of k plus 1 is true, the inductive step. The statement for all integers n greater or equal to a, P of n is true. The supposition that P of I is true for all integers I from a through k is called the inductive hypothesis. Another way to state the inductive hypothesis is that P of a, P of a plus 1, P of k are all true. We discuss about the applying strong mathematical induction. An integer greater than 1 is divisible by a prime number. If we discuss the proof, let the property P of n be the sentence P of n be the sentence n is divisible by a prime number. So this is the property n P of n. Show that P of 2 is true. To establish P of 2, we must show that 2 is divisible by a prime number P of 2. But this is true because 2 is divisible by 2 and 2 is a prime number. Show that all integers k greater or equal to 0 if pi is true for all integers. For k, then p of k plus 1 is also true. Let k be n integers with k greater or equal to 2, and suppose that I is divisible by a prime number for all integers I from 2 through k. We must show that k plus 1 is divisible by a prime number. Case 1, if k plus 1 is prime, in this case k plus 1 is divisible by a prime number, namely itself. If k plus 1 is not prime, in this case k plus 1 is equal to ab, where a and b are the integers, with a is in between 1 and k plus 1 and b is in between 1 and k plus 1. Thus in particular you can see that A is in between 2 and k. And so by the inductive hypothesis, A is divisible by a prime number p in addition because k plus 1 is equal to A. So we have that k plus 1 is divisible by A. And since k plus 1 is divisible by A, so A is divisible by P by the transitive property of divisibility. So k plus 1 is divisible by the prime number. Therefore, regardless of whether k plus 1 is prime or not, it's divisible by the number, the prime number. This was to be shown. Here is the same example. Prove an integer greater than 1 is divisible by a prime number. So here is the lecture summary which we have discussed in this lecture: sum of symmetric series, divisibility property, inequality, sequence property, and the example, and also we discuss about the strong mathematical induction. Thank you. Next time we will meet in lecture 11.